Okay, what we have here is we're going to start a session in Zoom together with a PowerPoint presentation, which I call a math lesson. And this lesson is on using phasors and complex numbers for electronic courses. Okay, let's recall first the algebra. From algebra, we've got a quadratic equation that is basically a function of y as a function of x, and really describes a parabolic curve such as y equal ax squared plus bx plus c, where the quantities a, b, and c are coefficients. They can be positive or negative scalar numbers. Y is the dependent variable, x is the independent variable. And like I mentioned, it's a parabola, as you can see on the graph. So if we create a, let's take a look at a particular equation. In this case, we have assigned numbers. A is 1, B is 5, and C is 10. And using that, plugging that into the y of x equation, we get the graph as shown in the graph there. And you'll notice that the graph crosses over the x-axis, okay? And where it actually crosses over the x-axis, those are the points where basically the y is equal to 0, okay? And those are solutions for that particular equations. And those solutions can be identified by the quadratic equation as we all know it, shown on the right-hand side here. X equal to minus b plus or minus square root of b squared minus 4ac. And all the quantity is divided by 2a. In this case, we get two solutions. They have a root 1 and a root 2. On the left, it crosses the axis at minus 6.531. And on the right, the crossover on the right is plus 1.531. So those are both solutions of a real equation. Now, switching that equation, changing that equation around, I'm going to change a few constants around, okay? In this case, we're choosing the constants a equals 1, b still equals 5, but now we're changing c to 20 instead of 10, okay? And we get a curve, as you can see, that does not cross the x-axis. Because it does not cross the x-axis, then you get solutions that are imaginary. In other words, you don't have positions where the equation actually resolves itself at y equals 0. Nevertheless, they are roots of the equation of y of x. In this case, if you put the numbers into the quadratic equation, you'll notice you get, in one case, we had our root 1, we get minus 2.5 minus 3.708 pi, and on root 2, minus 2.5 plus 3.708 pi, okay? So basically, they are symmetrical about the y-axis, all right? But you get two roots, and they're both imaginary numbers. So let's look at that again. Root 1 is minus 2.5 minus, and we're going to use, instead of I, we use the letter J because in electronics, I really signifies current. And so we want J to represent the solution to x squared equals minus 1. Okay, so J is actually the quantity of the square root of minus 1. So we've got the real, and there are basically our root 1 is in a rectangular form, with a real portion being minus 2.5, and the imaginary portion is a minus J 3.708, where the other root 2 is minus 2.5 and plus J 3.708. So the real portion, again, is minus 2.5, but the imaginary portion now has become a positive 3.708. And those solutions are complex values. We can figure out, using simple algebra, what the magnitude of that is by just taking the square root of, the x quantity squared plus the y quantity squared. So we've got the square root of minus 2.5 squared plus 3.708 squared. So we get a magnitude of 4.47. And then we need to get an angular relationship. So we take the y, the arctangent of the y portion divided by the x portion. So in this case for root 1, we got minus 3.708 over minus 2.5, which gives us a plus 56 degrees. So the polar solution then becomes the magnitude, which is 4.47, followed by the angle, which is 56 degrees. Whereas the root 2 angle then becomes out to be minus 56 and giving us a polar solution of 4.47, and the angle is minus 56 degrees. Okay, so what have we learned from all of this? We learned that algebraic polynomials are expressed, we use numeric values, multiplied those by exponential variables, such as x squared, x cubed, and so forth, to get a polynomial, and we get a summation. And we get a polynomial equation that needs to be rooted, needs to be resolved. While in electronics, we are likely to see these types of expressions. And we need to evaluate the certain dependent variables, such as voltage, current, or reactance values. The dependent variable depends, in most cases, on the value of the independent variables, as we see when we use the quadratic equation. Now, we're not limited. Okay, the quadratic equation is for second order polynomial, but we can have a third, fourth, and fifth order polynomial, and there are solutions that are quadratic-like for those equations, okay? So we use the like formulas, quadratic-like formulas, and in many cases, as we've seen, we can take root values that are dependent on coefficient values, and in some cases, the root value is a negative number. So when taking the root expression, we get, as I said, a square root of a minus a number, for example. So what's the square root of negative? Well, it's an imaginary number. So we take solutions from the algebraic equations and we get complex numbers, which are composed of a real portion and an imaginary portion. So we need to identify, okay, what is the meaning of a real and what is the importance of an imaginary portion. So we look at our electronics, and in electronics we have related, in the electronics related math, our real portion really implies that the quantity is not dependent on voltage current phasing, okay? So basically, voltage and currents are in phase, and that's resistor type reaction. Whereas imaginary portion really implies that there's a phasing relationship, and that could be a lead lag in the voltage and current, and that we know is shows up in our reactances, okay, such as 90-degree leading or 90-degree lagging. So let's go ahead and do some math to explain all of this, how this can all be done nicely. Okay, take advantage of this. In order to do that, let's really review where we are graphically, mathematically. Okay, electronics, we're going to deal with two-dimensional space. Now, basically, we have X and Y axes, two-dimensional. X meaning left and right, okay, meaning positive numbers to the right, negative numbers to the left. And Y is up and down, positive up, negative down, okay? And that is what we call a Cartesian coordinate system, first developed by René Descartes, who was a mathematician, philosopher that came up with a lot of really neat stuff, okay? So we're going to start out knowing the Cartesian coordinate system, which we are well familiar with by now. Mathematicians use that Cartesian coordinate system, and what they really call it is they call it vector space. And in fact, they're not limiting it to X and Y or two-dimensional space. They limit it to n-dimensional space, where you can have X, Y, and Z, and maybe a fourth dimension and so forth, which we're not able to draw, but we can work out mathematically, okay, using equations. So we're only going to stick to two-dimensional space. And in this case, as shown here, we create a vector. Any point in a two-dimensional space is represented by a vector that starts from the origin and goes all the way out to that particular point. That point has axes. In this case, what you see is a x-axis 3 and a y-axis 4. So basically, it creates a 3, 4, 5 right triangle, right? So V, the quantity V would be 5 probably, okay? And we can do that, create any kind of a vector. And there it is. We've got our vector is composed of a vector in the x direction and a vector in the y direction. Allows us to manipulate multiple vectors. Okay, in this case, you can see that we have two components. And the math from that comes very easily. We can take the vector v. If we had the vector, we started with the vector v, we can get its vx and vy components, knowing the angle, the direction angle theta of that vector, by vx being v times the cosine of theta, and vy being v times the sine of theta. And we know that the magnitude of v is vx squared, the square root of vx squared plus vy squared. That's all old stuff that we know. So instead of vector space, okay, we're going to use a Cartesian axis, but we're going to look at it from a complex space. Okay, the complex space then takes the Cartesian coordinates and creates the x-axis as a real axis and the y-axis as an imaginary axis. So we haven't really changed anything except the labels of real and imaginary. And again, we still have points that are designated by two values. And in this case, because it's imaginary, we're using the values 3, which is real, and J4, which is imaginary. All right. But again, the magnitude of V is still going to be 5. That is the square root of 3 squared plus 4 squared. But we can also say that the real of V is basically Vx, okay, which is V times the cosine of theta. And the imaginary part of V is going to be V times the sine of theta times J. In this case, J is a positive, okay, because theta is a positive. So luckily, we've got a way to express a rectangular method of expressing a complex expression, which, as you can see here, if we let Z be that complex vector, and we let A be the magnitude of that value of the vector, and we let theta be the vector directional angle, so we need magnitude, angle, and the resultant vector, then we can basically identify that vector Z in rectangular ways by saying that Z is equal A cosine theta plus J A sine theta, okay? Where we've got separated the real part and the imaginary part with a J. So there is our complex expression in rectangular form. Well, if you go to higher mathematics, okay, you'll find out that both the cosine and the sine functions can be expanded to an infinite series, okay, and that if you add the infinite series for cosine to J times the infinite series of the sine function, you end up getting the infinite series of an exponential or e to the x function. Okay, so e to the x is equal to cosine x plus j sine x. Okay, so we can basically rewrite it, okay, in terms of theta and j's. We e to the j theta is equal to the cosine theta plus j sine of theta. We again using j as the imaginary coefficient, imaginary portion of it. Okay, and e is a natural number. Okay, so that basically we can say at the bottom that a cosine theta plus j a sine theta is basically the same as saying a times e to the j theta. Okay, well, we like to abbreviate things and use things that are not really needed. So when we take the a e to the j theta, we just use the two numbers a and the j and the theta. Okay, so when we write a angle theta, we know that a angle theta is essentially a e to the j theta, or it's also A cosine theta plus J sine theta. Okay, so now we've actually reduced the amount of writing we need, okay, down to using the two basic figures, which are the magnitude and the angle. Those are the two identifying numbers that identify a complex number and a phasor and a vector. So what's the polar pros and the cons of the polar? Well, the pros for using the polar expression is that we know there's no need to draw vectors or phasors. So we cut out the drawing of arrows and whatever. But because we can now use e to the I theta, or a e to the I theta, then we can use the math rules that go around with exponentiation. So that multiplication is accomplished, as we know, is by adding the exponents, so that if you have a e to the fourth and b e to the fifth, then we get a times b, because you're multiplying it. And then you add the exponents, 4 plus 5. And similarly, exponentially or division-wise, we subtract the exponents. So we get, if we divide 10e to the sixth by 5e to the third, we get 2. 5 over 10 over 5 is 2. And e is 5, 6 minus 3, giving us 3. And the other thing is we will get either a positive angle theta or a negative angle theta, implying whether there's a leading or a lagging situation when we divide. And there's no need then to use trigonometric functions. Of course, the drawback on this is we don't have a picture, okay? Sometimes the picture is nice to have, okay? It really rationalizes, does that really look correct or not, okay? So that's what a picture does. And the other big drawback is that if you want to add or subtract, we can't do that exponentially, not easily. So we really rely on using vectors and phasors, and essentially then we use the rectangular form to do that. And then we can always switch from rectangular form to the polar form. The other last thing that we have to realize is that we need to remember the phase differences between voltage and currents, which I think we all know by now. Okay. Why do engineers like to use this method? Well, because the J term identifies the parameter as a reactive term, and we realize it's not a real term, but we identify that portion which is reactive and separate the reactive portion from the non-reactive portion, the real portion. And that else is everything, the efficiency is really dependent on an electrical circuit, is how real is, how close are you to have a resistive or real situation. So we know if we get something that's heavily reactive, and we know that how the more reactive it is, the greater the angle, the reactive angle. Okay, we can bring that back using a negative or an opposing circuitry to bring that closer to being real. And the exponential terms actually are solutions to higher mathematics, all right? If you recall, during DC, we've used a couple of ways of modeling the circuits, and what we ended up with simultaneous equations to solve for voltage and current, all right? And but we can't do that in AC because voltage and current are not always in phase with one another. So we are stuck with using, our equations then become differential in time. They become dynamic, okay? We use dynamic algebra, meaning it's ever changing because they're relative. We're looking at the relative changes of one component to the other. So the examples we have that we've already learned about is in the case of a capacitive current, for example, we know that the current on the capacitor is proportional to a quantity which we call dV dt, which is a differential number. Okay, it's a differential, how voltage changes with time. Okay. And in the case of an inductive, we use the voltage, how the voltage changes as a change in current in unit time. Okay, that's another differential. So we can create, we have a circuit that has resistance, has capacitance, and it has inductance. We're going to create a big polynomial in terms of real numbers and imaginary numbers. And we can, the real portions of that will be mostly resistive, and the imaginary portions are mostly reactive. So we can separate the two. And basically then what we use this for is when we have electronic circuits that feed electronic circuits, AC circuits that are feeding sensors, those sensors can be reactive or they can be resistive. Okay, by reactive circuit sensors, for example, ultrasonic sensors are reactive, and electromagnetic sensors, you know, are also reactive. So the feeding circuit has got to be created to create an imaginary type situation. And we use the imaginary portion then to investigate what the changes are in our reactive component, which is being either the ultrasonic sensor or the electromagnetic sensor. So that is our presentation for mathematical presentation on how we can use complex formulation to investigate AC circuits.